Derivatives of composite functions, the chain rule. Welcome to this lesson on the derivatives of composite functions, where we will be focusing on a powerful tool known as the chain rule. Before we dive into the calculus, we first need to ensure we have a solid understanding of what a composite function actually is. Let's look at our first slide. In mathematics, a composite function is defined as a function that is applied to the result of another function. To explain this more formally, imagine we have two different functions. U of x and v of t, we can form a composite function, f of x, by taking the entire expression of the function u of x and substituting it into the variable t of the function v. In your textbooks, you will see this denoted in two ways, either as f equals v composed with u, or as f of x equals v of u of x. In simpler terms, you can think of this as a function inside a function. To visualize how this works, remember that the inner function, u of x, is processed first. Once we have that result, its output becomes the input for the outer function, v. Understanding this inner and outer relationship is essential, as it provides the foundation for the chain rule, which we will define in the very next slide. The chain rule defined. Now that we have established what a composite function is, essentially a function inside another function, we can move on to how we actually differentiate them. This brings us to the chain rule. The chain rule is a fundamental formula used specifically to find the derivative of a composite function. Its primary purpose is to allow us to differentiate a complex function by breaking it down into its simpler, more manageable components. To understand how this works, let's look at the logic. Suppose we have a function y equals f of x. If this is a composite function, we can define it such that y equals v of u, and u equals u of x in this scenario. The derivative of y with respect to x is calculated as the product of the derivative of v with respect to u and the derivative of u with respect to x. In formal mathematical terms, this formula is expressed as di dx equals di du multiplied by du dx. Alternatively, if you are using function notation, you will see it written as the derivative of v composed with u of x equals v prime of u of x multiplied by u prime of x. While these formulas may seem abstract at first glance, they represent a very logical sequence. To help you visualize this chain of events more intuitively, we will look at a real-world analogy involving a gear system in the next slide. Real-world analogy, the gear system. Now that we have looked at the formal definition and the mathematical formula for the chain rule, let's take a moment to understand the intuition behind it, so it feels less like a formula and more like a logical process. To visualize this, imagine a mechanical system consisting of three connected gears: Gear A, Gear B, and Gear C. In this system, the movement is sequential. If you turn Gear A, it causes Gear B to turn. Subsequently, as Gear B turns, it causes Gear C to turn. Now, if you want to determine how fast Gear C is rotating relative to Gear A, you cannot simply look at the two of them in isolation. Because Gear B is the intermediary, you must multiply the rate at which Gear B turns relative to Gear A by the rate at which Gear C turns relative to Gear B. In the world of calculus, this rate of change is exactly what a derivative represents. Therefore, the chain rule is simply the mathematical way of multiplying these rates of change across a chain of functions. By understanding this relationship, it becomes much clearer why we multiply the derivative of the outer function by the derivative of the inner function. With this intuitive understanding in place, let's move forward and look at the practical, step-by-step process for applying this rule to actual problems. Step-by-step process for differentiation. Now that we have a conceptual understanding of the chain rule and the gear analogy, let's look at the practical application. To differentiate a composite function, I recommend following these 6 manageable steps to ensure you don't miss any part of the process. First, identify the inner function. This is the expression tucked inside another operation. For instance, look for terms inside a square root, inside a trigonometric function, or inside a power. For the sake of our calculations, we will label this inner part as u. Second, identify the outer function. This is the overall operation being applied to that inner part. We can represent this as v of u. Third, differentiate the outer function. Here, you find the derivative of the outer function with respect to u. The key here is to treat u as if it were a single, simple variable. This result is what we call dv over du. Fourth, differentiate the inner function. Now, focus only on the expression you labeled as u and find its derivative with respect to x. This gives us du over dx. Fifth, multiply the results. Just as we saw in the formal formula on the previous slide, you multiply these two derivatives together, dv over du multiplied by du over dx. Finally, substitute back. Since our original problem was given in terms of x, we must replace all instances of u with the original inner expression to arrive at our final answer. Once you have mastered this sequence, the process becomes very systematic. Let's put these steps into practice with the worked examples in the next few slides. Worked examples, Example 1. Now that we have established the theoretical foundation and the gear analogy, let us apply the step-by-step process to a practical problem. We will begin with Example 1, which focuses on a basic trigonometric composition. Our objective is to find the derivative of the function f of x equals sine of x squared. Following the process outlined in the previous slide, step 1 is to identify the inner function. If we look at the expression, the part nested inside the sine operation is x squared. Therefore, we define our inner function, u, as x squared. Step 2 is to identify the outer function. By treating the inner expression as a single variable, u, we can see that the overall operation being applied is the sine function. Thus, y equals sine of u. Now we move to step 3, where we differentiate the outer function with respect to u based on our standard trigonometric derivatives. The derivative of sine of u is cosine of u. This gives us dy by du equals cosine of u. In step 4, we differentiate the inner function with respect to x applying the power rule to x squared. We find that the derivative is 2x. So, du by dx equals 2x. Step 5 is where we apply the chain rule formula we discussed earlier. We multiply the derivative of the outer function by the derivative of the inner function. This gives us dy by dx equals cosine of u multiplied by 2x. Finally, in step 6, we must ensure our final answer is expressed entirely in terms of x. We substitute the original expression for u, which was x squared, back into the equation. This results in dy by dx equals cosine of x squared multiplied by 2x. For a cleaner final notation, we typically write this as 2x cosine of x squared. Notice how we differentiated the outer function while keeping the inner part exactly as it was before multiplying by the inner derivative. This is a critical detail that we will explore further when we discuss common mistakes in the upcoming slides. Worked examples, Example 2. Moving forward to Example 2, we will examine a power and algebraic composition. Our goal here is to find the derivative of the function f of x, which is equal to the square root of x squared plus 1. Following the step-by-step process we established in the previous slides, we begin with step 1, identifying the inner function. In this case, the expression nested inside the square root is x squared plus 1, which we will define as u. Next, in step 2, we identify the outer function. To make the differentiation easier, we can rewrite the square root of u as u raised to the power of 1/2. So, our outer function, y, is equal to u to the power of 1/2. Now we move to step 3, where we differentiate the outer function with respect to u by applying the power rule. We bring the exponent down and subtract 1 from the power, resulting in 1/2 u to the power of minus 1/2. This can be further simplified to 1 over 2 times the square root of u. In step 4, we differentiate the inner function with respect to x. The derivative of x squared plus 1 is simply 2x. For step 5, we apply the core logic of the chain rule by multiplying these two results together. This gives us the derivative of y with respect to x as the product of 1 over 2 times the square root of u and 2x. Finally, in step 6, we must substitute the original expression for u back into our equation to ensure our final answer is in terms of x by replacing u with x squared plus 1. The 2 in the numerator and the 2 in the denominator cancel each other out. This leaves us with our final result, x divided by the square root of x squared plus 1. While this process is logical, it is easy to overlook a step. In the next slide, we will discuss some common mistakes to avoid so that you can double-check your work during exams. Common mistakes to avoid. Now that we have walked through the step-by-step process and seen some worked examples, it is important to discuss some common pitfalls. Let's look at the most frequent mistakes students make when applying the chain rule. First, let's address the error of differentiating both functions simultaneously. A common mistake is attempting to differentiate the outer and inner functions at the same time. For example, if you are finding the derivative of the sine of x squared, you might be tempted to incorrectly write the result as the cosine of 2x. To correct this, remember the rule. You must differentiate the outer function while keeping the inner function completely unchanged, and only then multiply that result by the derivative of the inner function. Second, many beginners simply forget the inner derivative. It is quite common to differentiate the outer function, but forget to multiply by the derivative of u with respect to x. For instance, if you have the expression 3x plus 1, all raised to the power of 5, a student might incorrectly state that the derivative is 5 times the quantity 3x plus 1, raised to the power of 4. To avoid this, always remember to close the chain by multiplying by the derivative of the inside. In this case, you would multiply by 3, resulting in the correct answer of 15 times the quantity 3x plus 1, raised to the power of 4. Finally, we have the issue of incorrect substitution. Sometimes, students substitute the value of u back into the expression too early or too late, which often leads to algebraic confusion. The best way to prevent this is to keep your variables, u and x, distinct and separate until you reach the final multiplication step, just as we practiced in our previous examples. By staying mindful of these 3 common errors, you will be much more confident in your calculations. Now, let's move to the final slide to summarize our key takeaways. Key takeaways. To wrap up our lesson on the chain rule, let's go over the key takeaways to ensure you have a solid grasp of the concept before we move on to more complex problems. First, let's remind ourselves what a composite function is. As we discussed at the beginning of the session, it is essentially a function inside a function, which we represent mathematically as f of x equals v of u of x. Next, let's revisit the formal chain rule formula. The derivative of y with respect to x is equal to the derivative of y with respect to u, multiplied by the derivative of u with respect to x. This is the mathematical chain that allows us to link the rates of change together, much like the gear system analogy we explored earlier. If you find the formula difficult to memorize, just focus on the core logic we applied in our worked examples. Always differentiate the outside function first, keeping the inside expression exactly as it is, and then multiply that result by the derivative of the inside function. This step-by-step approach is the best way to avoid the common mistakes we just discussed. Finally, it is important to understand the application of this rule. The chain rule is an essential tool in your calculus toolkit. You will need it whenever you differentiate trigonometric, logarithmic, or exponential functions where the argument is not a simple x, but rather another function entirely. Keep these points in mind, and you will be well prepared for the upcoming practice exercises.